All right, folks, it's time to get into the meat of General Chemistry 2. I hope you reviewed bonding, and if you haven't, go back and look at the last video. We're going to talk about intermolecular forces. Intermolecular forces, forces between molecules, are the reason anything can become a liquid or a solid. And that's the next two things we're going to study after intermolecular forces. So, we're going to have a three-part series on intermolecular forces, and today we're going to talk about ionic forces, forces between a positive ion and a negative ion in compounds we call colloquially salts. So let's get into it right now. Boop. Well, hi everybody. Hi, Mike here, and we're going to talk about intermolecular forces. So let's do so. First of all, you'll often see intermolecular forces abbreviated IMF, and so that will save you 17 seconds every semester if you just call them IMF. Of course, I'll probably just call them intermolecular forces because knowing my luck, someone will try to skip my heartfelt intro and come in at 3 minutes and be like, what's an IMF? Yeah, but anyhow, okay. So let's talk about what intermolecular forces are in a very general sense. Intermolecular forces are the result of Coulombic attractions, that is, positive charge is attracted to negative charge. And there's about three classifications of why that could be. Now, take a look at this diagram right here. Now, I got that from the OpenStax book. I find it a little bit confusing because you'll notice in that diagram there was kinetic energy going one way and intermolecular forces going the other way, showing that they sort of counter each other. But the bottom line is kinetic energy and intermolecular forces aren't related at all. So let's talk about the solid state of matter. Okay, let's make a little diagram here. You all know what a solid looks like. So this is the state that is solid. And let's only talk about kinetic energy. So kinetic energy is related to temperature. And as you increase the kinetic energy, we're going to say this is going to be increasing kinetic energy. Kinetic energy increase. Fair enough? Now what will happen is there's a barrier in energy, and every solid, every substance has its own unique amount of energy in which the solid will then become a liquid. Now you can think of anything in your mind. Think of water, or it could be candle wax. But if you take enough kinetic energy out of it, it will solidify. And if you put enough energy into it, it will liquefy. And you might recognize from Gen Chem 1, that quantity is called the delta H of fusion. And you will convert the solid to a liquid. Liquids are able to have more freedom of movement at the molecular level, and that's because now what we're going to do is we're going to, if we put more kinetic energy in, you will actually have solid particles. They're sort of locked in place in a thing called a lattice or a crystal structure, and they're rattling around. But if you put enough energy in now, the layers of molecules can kind of slide along each other, and you'll have a liquid. And if we increase the kinetic energy more, you will have a gas. So, all substances can occupy these three phases, and if you think about intermolecular forces as a sort of energy barrier, by the way, that's called delta H of vaporization. And of course, you might recognize that that direction's positive and that direction's negative. So that's a little bit of review for free, no charge for that. But what happens is if you go and increase kinetic energy, you will find that you have the ability to defeat the intermolecular forces. So that's kind of a thing holding them in the state where they're attracted to each other, but at the gas level, at the gas state, the molecules are moving around relatively independent of each other. So the other thing in the textbook was a little confusing because it says, well, what if intermolecular forces were to increase? And the reason that's confusing for people is because you would have to then switch out what the substance was. So let's say we're like at room temperature, and we are, we're talking about water. Water is primarily at that point in kinetic energy. And if you were to go and switch that out for something like table salt, you would find that it'd be a solid. So basically, if you're going to change the intermolecular forces, you have to change what the substance is. So that's why that's confusing. So you can think of it, change one variable at a time in your mind. So you could say, hey, here's an ice cube. And if I go and increase the kinetic energy from the temperature of a freezer to room temperature, it'll liquefy. And if I go take all those ice cubes that melted and then I put more kinetic energy in, it'll become steam. So that's one way you can think of it. Or you can think of, well, if I was at a fixed point, at a fixed temperature, I could take something that had very strong intermolecular forces, like table salt, and it would be a solid. And something with a little bit weaker intermolecular forces would be a liquid. And something like CO2 would be a gas. So just don't change both variables in your mind or you'll go crazy. All right. Now, buckle up, because the next thing we're going to talk about is ionic forces. You've talked about ionic bonding, and actually you'll notice that the textbook that we use, the OpenStax textbook, does not include a section on ionic bonding because it's arguably not an intermolecular force. It's sort of a force between or within a molecule, so it's complicated. We'll talk about solids later. Ionic compounds are primarily solids, so you can say, well, they must have very strong intermolecular forces. So this part is not in your book, but you're getting it for free, no charge at all. So let's go ahead and take a look at the size of cations. Those are the positive ions, cations, and anions. Cations are positive, anions are negative. And let's take a look at this figure that I stole from the internet. All right, by the way, when I say I stole something from the internet, it's usually just a fun term I'm using. I use all royalty-free stuff whenever I quote-unquote steal. I got a nasty review on one of my professors. He said that he stole something from the internet. I didn't really steal it. It's public domain. Okay, but what you saw there is that positive ions are generally smaller than negative ions. Why is that? Well, in a positive ion, you've got more protons than electrons. So if you took something like sodium, this would have 11 protons, 10 electrons. And that would have a radius, and I looked this up, 116 picometers. If you were to take something like chloride, that would have 17 protons and 18 electrons. Now, to really understand intermolecular forces and stuff like radius of an atom or an ion, you have to use your imagination. So try to figure out in your mind, what do you think would be a bigger thing? A positive ion with 11 protons in the nucleus. And by the way, what holds the electrons there is the protons, right? Remember I said Coulombic forces, positives attract negatives. So something with 11 protons drawing in 10 electrons, or something with 17 protons drawing in 18 electrons. Well, you think about it, the more protons there are, the more they're going to kind of suck in the electrons out in the outer cloud, and especially those outermost ones. And that's why this anion, chloride, is significantly bigger than the positive ion. And generally you're going to say maybe there's some weird instances where an anion might be smaller than a cation. If you were like taking something like rubidium way down at the bottom of the periodic table, it has so many quantum levels that it could be possibly bigger than something like fluoride. But most of the very common things, like right here we're talking about table salt, you'll find that the positive ion is smaller than the negative ion. So there you go. Let's make a little picture of that. So I'm going to take sodium chloride, and we're going to make a picture of something that is, 100 and they're circles, they're spheres, right? And what you got is you got a positive charge there in the nucleus. Let's make something that's slightly bigger. So that would be like sodium chloride. Now this repeats all over the place, and we'll get into that, but let's just not worry about that yet. So what you got is you got the electron cloud is where that negative charge is. The nucleus is where that charge is. So you got this charge, +1, -1, and you got a distance. We'll call that d. And those forces in ionic compounds are extremely small, or extremely large and strong, because you got big charges, +1, -1. All right, and then they're very, very close together. They're practically almost touching each other. Now, the positive charge is buried in the nucleus, and the negative charge is out in the outer shell. So that explains why ionic compounds A are solids at room temperature exclusively, but B, we're going to find out that it's really hard to separate them, and it takes a lot of energy. So let's go, and I dug up the melting point of this. That's what thing we're going to talk about. Melting point is 801 degrees Celsius, not Fahrenheit. So that's a really strong force. And the really strong intermolecular forces are the fact that you've got big, full-blown charges that are +1s, +2s, -1s, -2s, And so these are very, very, very tightly stuck together substances, all right? And now, let's do this. What if I were to switch out a sodium for a potassium? Potassium would have 18 electrons, and it would have 19 protons, but this would have a radius. I looked this up. This is not, secret information. You can go just Google the ionic radius of potassium, and you'd find out it's 152 picometers. So what if we had potassium chloride? That potassium would be a little bit bigger. Those charges would still be a +1, -1, but the fact is they can't come in as close a proximity. The +1 would be a little bit further away than the -1 of the chloride, and so when you look up its melting point, that would be huge still, but not as huge as sodium chloride. So that's the whole deal, folks. What we're trying to do is explain why things have the properties they do. Melting point is the way you could identify something. Heck, you could go stick something in a tube. In organic chemistry, they do this all the time. And as soon as you synthesize a compound, you test how pure it is or what its identity is by its melting point. So that's kind of a thing that is very reproducible, and we're going to talk about melting points further on out. Let's take and switch the other variable. So we change size. Now if you go back to Gen Chem 1, magnesium oxide. Now magnesium is the neighbor of sodium, and oxygen's pretty darn close to, well, it's a little bit smaller than chloride. Because it's one of the periods up further. It's in the second period, but still, so you've got about the same size as sodium, smaller than chloride. But if you were to look up that and its melting point, what would you think it would be? Well, remember, That's a +2. That's a -2. And so what sticks together better? A +1 and a -1, or a +2 and a -2? Yeah, you're right. A -2 and a +2. So this is going to be a melting point of 2,852 degrees Celsius. That's a huge temperature. And you might remember, if you ever taken a piece of magnesium and burned it, you get this white powder at the bottom. It kind of looks like ash. That's magnesium oxide. It's extremely stable. And as a matter of fact, I don't even think it melts. It decomposes before it melts at like 2200 or something. And so basically, folks, the closer you can get the charges and the bigger the charges are, the higher the intermolecular forces. And by the way, all these melting points we've been talking about have been certainly higher than room temperature. And so you see why we're not really going to talk much about ionic bonding until we get to solids, because it takes a huge amount of energy. You ever have an inflammation or something like that and want to soak yourself in Epsom salts? That's magnesium sulfate. And now what will happen is magnesium will still be the same ion, but if we switch it out for a bigger negative ion like a sulfate, you'd find out that those charges, although they're big, can't quite get as close to each other. And this is 1,124 degrees Celsius. Still huger than potassium chloride, sodium chloride. You know, sodium chloride's table salt. This is a table salt substitute. There's Epsom salts. So these are all things that are, you know, not military secrets. These are things, compounds that touch your life. And so here's my task for you. Could you take a bunch of compounds, figure out how big the ions are, and then also what the charges of the ions are, and sort them according to increasing or decreasing melting point? I hope the answer is yes, because that's what you're going to have to do. All right, one more thing. I'm trying not to make this too long. To conclude ionic bonding, we're going to talk next about a quantity called lattice energy. So let me talk about lattice energy. You might have already studied that in Gen Chem 1 if you talk about the Born-Haber cycle. But what happens is there's sometimes when we're going to talk about ionic bonding in greater detail, lattice energy is, let's say that this was sodium chloride. It would actually be the energy required to totally vaporize a solid. So make that a gas. And that's just kind of a theoretical energy to say, well, what would happen if we totally overcame the intermolecular forces of sodium chloride in its crystal structure. The crystal structure is called a lattice. And so that would be, by the way, the same kind of sort of trend that we'd say. You see NaCl, it would be 786 kilojoules per mole. By the way, you might see it negative. That means you go the opposite way. You could see it done either way. Here it's positive, so that would be input of energy to make a mole of sodium chloride then vaporize. So that's why that's such a huge number. Now, potassium chloride. That potassium ion is bigger, and so it would therefore require less energy to separate the charges, and you'll find out that the literature value of that is smaller. So it's sort of the same trend as melting points. Here's magnesium oxide, and I looked all these up. They're on Google or Wikipedia or something like that. And magnesium oxide, being much, much greater charges, is much huger in lattice energy. So there's another theoretical energy beside melting point. Melting point's more relatable. You know how a melting point works. You heat something up to the temperature where it becomes a liquid. But lattice energy, it sort of encompasses all the intermolecular forces of taking that liquid and then vaporizing it. All right, folks. We got 2 more lessons in IMF, intermolecular forces, because next time what we're going to talk about are polar compounds, where, by the way, you don't have full-blown positives and negatives, you have partials. So, for example, in a water molecule, you'd have a partial positive on the hydrogens and a partial negative, and partial is less than full-blown positive one.